Good evening, everyone. So I welcome you to this live interaction session for the course Introduction to Abstract Group Theory. So uh, let me share my screen. Uh, I hope it's visible. So are there any doubts? So we are supposed to discuss the solution for assignment 2 and assignment 3. Before that, if you have any doubt in the uh, course lecture notes or any of the practice assignment, you can ask. Otherwise, I will just start with assignment 2 solution.
Sir, I have a doubt from practice assignment 4, but I suppose we'll discuss, practice assignment, practice assignment 4, but I suppose we'll discuss them anyway after discussing assignment 2 and 3, right?
Yes. So what is the last date for that submission?
Tomorrow is the last date.
Okay. So maybe let's first discuss assignment 2, and then before assignment 3, we will see practice assignment 4.
Okay, sir.
How many questions you want me to discuss from that part?
There's one question which I'm unable to find the solution yet. So.
Okay, then I think we will have enough time for that. We will discuss it after discussing this assignment 2 solution. Okay.
Okay, sir.
So here is first question from assignment 2. We need to determine in which of the following cases the set H is a subgroup of the group G. Okay. So the first one is when G is the set of integers with addition and H is the set of multiples of 100. So whether it forms a group or no.
It's a subgroup.
It forms a group. Why?
So it's a form NZ, and so okay, so it's closed, and the identity belongs to the subgroup, and the inverse also exists within the subgroup itself.
Okay. So H is just in notation. I am following the class notation. So this is just 100 multiples of integer set containing all the 100 multiples. So it is of the form 100 times some x, where x is inside z, right? So as Pranjana pointed out, it satisfies all properties of a set to be a subgroup. So namely, first is identity is inside that, right? We can just take uh, x to be 0, and if 100x and 100y both inside H, then their sum will also be inside this set, which is just 100 of x plus y. That is also inside H. So it's closed as well. And inverse is just you take 100 of minus x. So if 100x belongs to H, then 100 of minus x belongs to H, and their sum will give us 0. Okay. And you have already seen in class that in fact this 100 has nothing to do. All subgroups which are of the form sum A times Z are subgroups of the group of all integers under addition. So in fact, for any n belongs to Z, looks like X. Fact for any n belongs to Z, the set NZ is a subgroup of Z. So that we have already seen. Okay. Okay. What about the second part? G is the group of non-zero complex numbers under multiplication, and H is the set of roots of the polynomial x cube minus x square plus x minus 1.
This is not a subgroup.
This is not a subgroup. Good. So G is in just C star, right? C star under multiplication. C star under multiplication. And H is set of solutions of the equation x cube minus x square plus x minus 1. So what is this set?
So it contains one I and minus I.
So this implies H is 1 I and minus I, right? And this is just very simple. This is just to take x square one side and uh, it will be just x minus 1 plus 1 x minus 1. So it is x square plus 1 and x minus 1. So this is having solution as 1, and this equation is satisfied by iota and minus iota. So that is just the set H. Good. So why it is not a subgroup?
So I belongs to H, but I square is minus 1, which doesn't
Very good.
belong to
So
H.
since I belongs to H, but means I belongs to H, but I dot I, just a second. But I dot I, that is I square, which is minus 1. This is not inside H. So H is not a subgroup of C star. Good. Now, what about the next one? S4, the symmetric group on 4 letters, and H is the one which contains the identity map and all the permutations which permute exactly 2 indices. Means just the 2 cycles and identity. So C is G is S4 and H is identity map, or I should write like this. Identity map union the set of all 2 cycles. Okay, so I can just take the 4 symbols to be 1, 2, 3, 4. So it is just the 2 cycles which permutes the A to B and B to A, and all other things are fixed. Fine. So is it a group? We have already discussed this in one of the practice assignment, I guess.
Yes, sir.
So whether it's
So
a
this
subgroup,
was discussed through if we take 1, 2 and 1, 3, then we have 1, 2 times 1, 3 to be 1, 3, 2. So this is not closed.
Right. So A for 1, 2, and even this comma is not needed. Just this thing is found. 1, 2 and 1, 3 both are inside H, and their product, which is 1 going to 2 and 2 is not here, so 1 will be mapped to 2. 2 is mapped to 1, 1 is going to 3. So 2 will map to 3 and 3 is mapping to 1. So this is a 3 cycle which is not inside H. This implies H is not a subgroup of G. Okay. Now, what about the last one? G is the group of non-zero real numbers under multiplication, and H is the set of all powers of integer powers of 2. So D is G R star and H is 2 raised to n, where n is inside the set of integers. So is it a subgroup?
Yes, sir.
Any guesses? The others can also speak. Don't worry if your answer is wrong, that's fine. But at least try. So is identity there?
Yes, sir.
Why?
So, 1 belongs to H since 2 plus 0 is 1.
Yes. So this is inside H. What about uh, the closer? See, 2 raised to A and 2 raised to B are in H. Then what about 2A times 2B?
That's just 2 power A plus B. And A plus B belongs to the set of integers. So, this is closed.
Right. So 2 times A plus B. This is inside H. So it is closed. Right? Now what about the inverse? Of course, we must also write that since A and B are inside Z, so A plus B is also inside Z, so this element is inside H. So that part I'm not writing here, that is trivial. So now what about this? If 2A belongs to H, for some A belongs to Z, then what about its inverse? 2A inverse is just 1 upon 2A, right? So we write Z. And what is 1 upon 2A?
2 power minus A.
2 power minus A. And this is again inside H, because A is an integer and minus A is also an integer. If the numbers would be varying over the non-zero integers, then there would be a problem. But here it's fine. Okay. So this implies H is a subgroup of G. What about the... So are there any doubts in this question?
No doubt.
Okay, so if that is there, it's fine. Then I will uh, move to the second question. Let A be the number of subgroups of order 2 of S3 and B be the number of subgroups of order 3 of S3. Choose all the correct statements. So how many subgroups of order 2 are there in S3?
3.
3. Why?
So there are 3 elements of order 2. So
Okay.
um, and since the order is 2, they are their own inverses, so they all form the subgroup. So identity and 1 2 is a subgroup. Again, identity and 1 3 is another subgroup. Identity and 2 3 is another subgroup.
Okay. So first, let me just tell you that if uh, for a group G, number of subgroups of order 2 is same as number of elements of order 2 in G. Okay. For any group G, number of subgroups of order 2 same as the number of elements of order 2 in G. Why? So let let us give say this is a set say A and it's very bad notation. Let me denote this set by some say A and this set by some notation B. So let H is some subgroup of order 2 inside this group. So then H is equal to some E times A, sorry, E and A uh, for some so then your subgroup must contain identity and there is one more element, right? So H is just E and it has just two elements, E and A. For some A belongs to uh, A non-identity belongs to G, right? Now, since A is inside H, or it's a very bad notation because I am not denoting this set by A, so elements of H should be denoted by small h. Okay. So, since H is inside H, therefore H square should also be inside H. Now, this can be either uh, there are two possibilities. This implies H square equal to E or H square equal to H. But this particular case will implies H is equal to identity, which is a contradiction, right? So this should be correct And this implies H is inside B, right? B is the number of elements. Oh, uh, just so there is a issue here. So A is a number, it's not a set. So I should not write like that. Hmm, maybe I can write it like that. Just some notation change I am doing. I should write one more line before it. Let A be the collection of subgroups of, or maybe since we have less space, I will just simply write like that. Let G be a group. Let A is all subgroups of G such that order of H is 2 and B be all uh, elements in G such that order of G is equal to 2. Okay. So then this will also be simplified. Claim is size of A is same as size of B. Okay. Remember here, I am not writing G belongs to G such that G square equal to identity. Because identity itself also satisfies that. But identity is not an element of order 2. That's why I'm writing all G belongs to G such that order of G is 2. Okay. So here is a proof of this claim. So for any H is inside A, we find an element H inside B. So this implies size of A is, or if you want, I can be a bit more rigorous. For any capital H inside A, there exists a unique small h inside B. So thus size of A has to be less than equal to size of B. Now, uh, what about the other part? I should not write this unique part is also fine. What about the other thing? Let H is inside B, then H square equal to identity and the subgroup generated by H, that is just H and identity. This is inside your A because it's a subgroup of order 2. So size of B is less than size of A. And combining both things, we will get that A is equal to B, size of A is equal to B. Thus, now coming back to our question, we get that hence for S3, there are 3 subgroups of order 2. What are these? Identity, as pointed out by Pranjana, identity 1, 2, identity and 1, 3, and what is the next one? Should write identity like this. Third one is identity and 2, 3. Okay. But the same thing doesn't hold true for subgroups of order 3. And you have this particular group as an example. So what about number of subgroups of order 3 in S3?
That's only one.
There is only one. So A equal to 3 is correct and B is A minus 2. That is correct. So what is that subgroup?
Identity
Hmm.
1, 2, 3 and 1, 3, 2.
There is a unique subgroup of order 3 in S3, that is identity 1, 2, 3 and 1, 3, 2. Very good. Because if 1, 2, 3 is there, its inverse has to be there. That is just 1, 3, 2. And these are just the two elements of order 3. So the subgroup generated by 1, 2, 3 is also this, and subgroup generated by 1, 3, 2 is also this. Okay. Good. Shall we move to the next question?
Yes, sir.
Yes. So we are supposed to choose all the correct options. G is an abelian group, then all its subgroups are also abelian. Is
This
it?
is true.
This is true. Why?
Um, Suppose H is a subgroup of G and some elements A and B belong to H. Since A and B also belong to G, A times B equals B times A. So
Good. So
this is true for all elements in the subgroups.
right. So commutativity is preserved by subgroups. That means if H is subgroup of G and AB belongs to H, then AB are also inside G. This implies AB is equal to BA because they are inside G and G is an abelian. So this should be, this should hold for AB as an element of H as well. Okay. Now the center of S3, the symmetric group on 3 letters has order 1. And the third part is the center of S3 has order at least 2. So what you say?
So the second one is true.
Second one is true. Why? So claim is center of S3. So I hope this notation is fine with you. Z of G means just center of that uh, group. So this is just the identity permutation. So we need to discard the possibilities that other elements are not inside the center. That means for each non-identity element, we need to find some element with which it doesn't commute. So for proof, let us take some uh, two cycle. So let A comma B, or just this A comma B notation is not very common, so I will write just AB belongs to S3. Okay, it's a permutation in two letters. Okay, now what? We need to show that for this element, there exists an element with which it doesn't commute. Take AC belongs to S3. Okay, so let me first clarify what is A and B. Just give me a minute. I need to plug in my charger. So let AB belongs to S3 for some A not equal to B, and AB belongs to 1, 2, 3. Okay. So this is some element of S3, maybe 1, 2, 2, 3, or 1, 3, anything. Then we will then take AC belongs to S3 for C not equal to B. So there are three indices, right? So you have chosen any two indices in AB. Now take the third one, and with that take the two cycle AC. Then this will implies AB time AC is what? A going to C, C is not here, and then C is going to A, and A is going to B. So this will be A, C, B. B is going to A, so this will closed. And what is AC, AB? This is A going to B, B is going to A is going to C, so this is ABC, and C is going to A again. This will close. And these two are distinct cycles, right? And ACB is not same as ABC in S3, because their order is not, they are not in cyclic order. A, B, C, if it would be uh, BCA or something, then it's fine. But the order is changing. So it's like 132 and 123. They are not same in S3. So this implies two cycles are not in the center of S3, right? Because for each two cycle, there is another element in S3. In fact, that's a two cycle with which it doesn't commute. So, but still there are two more elements, 1, 2, 3 and 1, 3, 2. What about them?
They too don't belong to center.
So let 1, 2, 3, even not to take 1, 2, 3. And just take for 1, 2, 3 belongs to G. See, 1, 2, 3 will definitely commute with 1, 3, 2 because 1, 3, 2 is the inverse of 1, 2, 3, and every element commute with its inverse, right? So we need to take a 2 cycle with which it won't be commuting. So in fact, if you take any 2 cycle, I think that will do the job. So for 1, 2, 3 belongs to G, take 1, 2 inside G, and then 1, 2, 3 times 1, 2. That will be what? 1 going to 2 and 2 is going to 1 again. So 1 will be fixed. 2 is going to 1.
To 3, right?
Oh, sorry. 1 is going to 2 and 2 is going to 3. So 1 will map to 3. 2 is going to 1 and 1 is going to 2. So 2 is fixed and 3 is mapping to 1. Oh, sorry. 3 is mapping to 1 again. So this will closed. And 1, 2 times 1, 2, 3. What about this? Whether we are getting the same 1, 2, 1 going to 2 and 2 going to 1. 2 will be fixed again. Sorry, 1 will be fixed again. 2 going to 3. 3 is not there. And 3 is going to 1. 1 is going to 2. Right? You can check the calculation. I think it's correct. This implies,
Correct.
yeah, 1, 2, 3 is not inside center of S3. Here also I should write S3. We are given explicit group. So we should write that. Similarly,
Sir, you mean this does not belong?
right. Thank you. For 1, 3, 2 belongs to S3, take 1, 3 belongs to S3 and check that they won't be commuting. So this will implies that 1, 3, 2 is not inside center of S3. So there is only one element, and what is that element?
The identity.
The identity. So this will implies center of S3 is just identity. So B is correct and C is not correct. This is okay, and this is not okay. Let H be the kernel of a group homomorphism, then H is contained in the center of G. Do you agree with that? No?
No, sir.
Then you have to give me an example.
Okay, so consider any non-trivial non-abelian group and take the zero map.
Take the zero map, everything mapping to 0.
Yes, sir.
Okay, very good. So you are saying take G to be any non-abelian, and what else you said?
Non-trivial.
So trivial is by definition non-abelian, right? So just a non-abelian group is fine, right? Trivial group is abelian, right?
Yes, sir.
Then center of G is of course not equal to G, right? And for any other group, for any, even the same group you can take for any group G prime, consider the homomorphism. phi from G to G prime, sending each element small g to identity of G prime, right? Then kernel of phi would be the entire group G, which is not inside, which is not equal to center. And in fact, so what it says? It says H is contained in the center of G. So here, this is this. So clearly, kernel of phi is not contained inside the center of G, right? Thus, the claim option is not correct. Okay, good. What about the next problem? Let me just paste it. So let S3 denote the symmetric group on three letters, and Z denote the additive group of integers. A be the number of sub group homomorphisms from Z to S3, and B be the number of 1-1 group homomorphism from Z to S3. C be the number of onto group homomorphism from Z to S3. Choose the correct statements. So we will be actually finding explicit value of A, B, and C, and then you can check that which of these relations are being satisfied. So what about the number of group homomorphisms?
There are six of them.
There are six. Why?
So, um, since it is a cyclic group, if I know where one maps, I know where the rest of the elements are fixed. So, one can either map to the identity, or it can map to the two cycles or the three cycles. So, there will
And
be
it can be mapped
six
to anything, right?
Sorry, sir?
So I'm just saying basically it can be mapped to anything,
Yes, sir.
right? So since Z is generated by identity, therefore any homomorphism, not identity, it's the element one, any homomorphism phi from Z to S3 is determined by phi of 1, and there are six elements in S3. So this looks like 50. This implies there are six homomorphisms from Z to S3. Okay. Now what about the 1-1 homomorphisms?
No. So it is infinite and S3 is finite, so it
Z3
can't
is
be injected.
since order of Z is greater than S3, therefore there is no 1-1 homomorphism. Because if there is any 1-1 homomorphism, then the order of the domain has to be less than equal to the order of the codomain. So therefore, there is no no 1-1 homomorphism from Z to S3. Okay, this implies B is 0. What about the onto part?
Again, the zero possible homomorphisms that way.
Huh?
So we can characterize all possible homomorphisms from Z to S3.
All positive.
All possible, all possible
All
homomorphisms.
possible. Right, right, right. So if phi is a uh, homomorphism from Z to S3, then image of phi will be nothing but the subgroup generated by phi of 1, right?
Yes.
Because why is it so? Since for any n belongs to Z, uh, phi of n is just phi of, I should write it more clearly. This is phi of 1 raised to n, means this 1 raised to n is in terms of addition. So this is just n times 1. But here the operation is addition. So I'm just writing it as 1 raised to n. So don't take it as integer multiplication, 1 power n. This means we are adding 1 n many times because here the operation is n, and which is pi of 1 raised to n. Okay. Maybe I should clarify this. This is n dot 1, not 1 raised to n in usual sense. So this is pi of 1 raised to n, and which is inside the subgroup generated by phi 1. Now, if phi is onto, then image of phi is S3, which implies S3 is cyclic. And this is a contradiction, right? Because S3 is not cyclic, even if it is not abelian. So, there is no onto homomorphism from Z to S3. This implies C is 0. Now, what about there is one more. Oh, so B, C both are 0. That is correct. A equal to 6. That is also correct. B plus C greater than 0. That is not true. A plus B plus C equal to 9. That is also not true. So last two options are correct. Okay. I hope that's clear.
Yes, sir.
Okay. Next question is, let G be a cyclic group. You need to choose the correct statements. If G is a finite group, then the order of G is a prime number. Is it true or false?
This is false.
Why?
So Z4 is cyclic, but the order
Very
is
good.
4.
So Z4 is cyclic, but the order is not a prime number. A is incorrect. For example, Z4 is cyclic, but order of Z4 is 4, which is not a prime number. What about the second part? Every subgroup of G is cyclic.
This is true, but
This is
I don't know how to prove this.
so. Let's see the proof then. B part is uh, so G is a cyclic group. Say let G be generated by some element. So we can take say A, okay, and H be any subgroup of G, right? Since it's a subgroup of G, it will also contain uh, powers of A, right? So let A uh, I be the minimum uh, positive integer such that AI belongs to H. Now see, G can be infinite also, but this index I, it's varying over integers, right? We will say A square, A cube, A4, and so on. So the index is varying over integers, and every subset of a positive integers has a least number, has a least positive number. So this minimum positive integer exists. So H will be a collection of powers of say some AI, AJ, AK, maybe A square, A cube, A5, A8, anything. And in negative direction also there will be the inverse of these positive powers. So, but if we just look at the positive powers, then there should be some minimum index I for which AI belongs to H. Okay. So this minimum index exists because every every subset of a positive uh, set of positive integers has a least number, has a least element. So we can take this I to be like that. Now the claim is the subgroup generated by AI is actually H. Okay. Now since AI belongs to H, therefore it's all of its powers are also inside H. So the subgroup generated by AI is also inside H. So one side is very easy. What about the other side? We need to all show that H is inside this uh, subgroup generated by AI. Means every element in H can be written as some power of A, right? So for other part, let H belongs to H, which is also inside G. Then H is equal to A raised to M for some uh, for some M inside Z, right? So because H has to be some power of uh, A, because G is generated by A only. Now, by division algorithm, what to say, just division algorithm or Euclid division algorithm maybe. Algorithm, there exists some integer kr belongs to Z such that M is I times K plus R. Why is it so? Because uh, one more thing we need to write. This is happening since I is minimum. Since uh, mod of M is less than equal to I, therefore this is happening. You cannot write uh, 2 as some kr plus r times of 5. Oh, sorry, the other way. Uh, you cannot write 2 as, or maybe this is also fine, I guess. Only problem is when we take it to be positive integers. Then I think there should be something right. So we need to take z inside z positive, right? So this is not possible if we are restricted ourselves to positive integers. But
Sir, is this modem less than or equal to, or is it the other way around?
small m,
Yes, sir.
any doubt?
Um, no. Why is it less than or equal to I?
It may be I itself, right?
Yeah, but how can it, when is it less than I? I is the least positive.
So it should be greater than equal to. Sorry, you are correct. Okay, now it's fine.
Yes, sir.
Only thing is whether we need this inside Z, I don't think so. Positive. What if I write -5? Then it should be minus. I take I to be 2, then it should be minus 3 hash and plus 1. So not both of them belongs to Z positive, but R is inside Z positive, such that this and 0 less than equal to R less than equal strictly less than I. So R should be positive, but K can be negative, right? So that's why this is needed, because as I said, you cannot write 2 as some K times 5 plus R if R is positive. Okay, positive and also less than 5. So that's why this is needed. Absolute value must be greater than equal to this, the absolute value of I. But I is already positive, so its absolute value is I itself. Okay. Now, this implies AM is AIK plus R, and that is AI times K and then multiplied with AR, right? Now, since AM and AI both are inside H, therefore, from here you can write AR is just AM times AIK inverse, right? So, so therefore, this thing AM times AIK inverse. Actually, this is just A raised to M minus IK, but I'm just writing it like that. This is also inside H, which implies AR is inside H, right? But AR is, uh, but the least positive integer for which A raised to something is inside H is I. So, but I is the least positive integer such that AI is inside uh, H, right? So, so R cannot be positive
Oh,
because
so
I
R
has to
can
be.
only be zero, right?
So R has to be 0, right? But I is the least positive integer such that AI belongs to the H. Thus, R has to be 0, which implies AM is just AI raised to K, and that means this is inside the subgroup generated by AI, and which implies H is inside subgroup generated by AI, hence they has to be same. So H is also cyclic. This implies H is a cyclic subgroup of G. So all the subgroups are cyclic. Clear?
Yes, sir.
Usually this proof is not there in books, I guess. They simply say that subgroup of cyclic is cyclic, subgroup of abelian is abelian.
This is a nice proof, sir. Thank you.
Um, this is like the most obvious thing that one should do. If you want to prove something is cyclic, you need to write everything as a power of some element, and you start with the minimum one and then show that it's actually the one that generates. So in many practices in algebra, uh, whether in ring theory or field theory or this, the minimum elements usually do the generation. So that's a very common trick. Okay. So every subgroup is cyclic. Now, this we have already seen in some practice assignment or somewhere, I guess,
Yes, sir.
right? If G is a uh, G to G is an onto-homomorphism to a group G prime, then G prime is also cyclic. So simply we can say if G is generated by A, then G prime is generated by phi of A. I don't know how I missed this part. I should not have told this in the interaction sessions because it was a part of assignment, but somehow I just did it. So every group of order 4 is cyclic, whether that is correct?
No. So the Klein group, I don't know if it's pronounced that way, but
Yes. So the
it's
counter
not.
example is uh, Klein group of uh, is the Klein group. Okay. Okay. Now let's see the last question of this assignment. Mm, Then I will discuss some problems which were there in the previous year assignment, which are similar to these problems. And then we will see your doubt in from practice assignment 4. Okay. Since those questions are closely related to these ones, so I just want to give you more examples, and that's why I will discuss them, and then we will move to practice assignment 4. Okay.
Okay, sir.
So final question is, we need to choose all correct statement. Z denotes the additive group of integer. First is for every group G, there exists a group homomorphism from Z to G. Is it correct?
Yes, sir. I can always define the zero home.
We can always define the zero map. So in fact, this is true for any two groups. For any two groups, G and G prime, there exists a trivial homomorphism. There exists the trivial homomorphism here exists the trivial homomorphism from uh, so even we don't require G prime to be G. So from G prime to G, any two groups, we can define a trivial homomorphism. So this is correct. If there is a group homomorphism, Z from G, then G is cyclic. That's not true because if G is non-cyclic and uh, the group homomorphism is trivial, and the group homomorphism is trivial, then uh, this is not true, right? Then this is this statement is false. Correct? Even we don't require the group homomorphism to be trivial. Any group homomorphism uh, will work. But I just want to say that there exists one group homomorphism, and so we need not to worry about the existence of a group homomorphism from a Z to a non-cyclic group. Okay. Now, what about the next statement?
That's also false.
For every group G of order at least 2, there exists one group homomorphism phi from G to uh, Z. So if it is 1, then what we should have? Let me just write. So if the homomorphism is uh, let phi from G to Z be a 1-1 homomorphism, then what is the problem?
So suppose we take some uh, group of order
This should
2.
be this, right? Order of G should be greater than equal to order of Z, right? But if we take G to be any finite group, any finite group, then this equality won't hold. Now this relation won't relation is not true. Hence, you have a counterexample. Any finite group will give you a counterexample. Any finite group of order, at least two. That means G to be any non-trivial finite group we need. Okay.
Excuse me, sir.
Yes.
I did not follow this proof. So why is the order of G greater than or equal to mod Z?
So if it is 1-1 map, then size of the domain should be at least the size of codomain, right?
Well, this is from G to Z, right?
I'm doing some mistake. Or is it the other way around? Right. It's from G to Z, so it should be other way around. Right. Thank you. So in Z, there should be at least G many elements, order G many elements, right? So mm, then we need to take some uh, group whose cardinality is more than Z. Maybe R will work, right? So for any group of size greater than Z, this relation is not true. So the statement is false. Correct?
Yes, sir.
Okay. Good that you were attentive. Now it says if let G be a, so this is false, and this one we have already done. So if G is a group of order at least two, and there is a 1-1 group homomorphism, then G is an infinite group. So uh, this one is also false, is it? There is a 1-1 group homomorphism from G to Z, then G is an infinite group. So this should also be false.
Sir, can you repeat what you said in the last few seconds?
What you are saying?
Can you repeat what you said in the last few seconds? Uh, there was some sort of internet connectivity
Ah.
issue.
So now we need to do the D part, which says same thing, but here it's saying that if there exists a one group homomorphism, then G is an infinite group.
This is true.
This is true, but in the previous one we have this equality. We- This is reverse direction, no? Or this is fine.
Sir, so for the uh,
This is
question
okay. This
C,
is okay. We can have the inclusion map. This should be okay, right? But then why this G should be infinite group?
so suppose suppose G is some finite group of order n.
Or maybe we can go with that generation property, right?
Yes, sir.
Hmm. Let phi is from G to Z be a one homomorphism. Actually, we should not talk about order. So this is infinite. So we should be writing this in terms of cardinalities. Cardinality of G is less than cardinality of. So if for a finite set, cardinality is just uh, the number, the size. But for infinite set, uh, the size doesn't really matter here. It's the cardinality which matters, right?
Sorry, sir, what's the difference?
So difference is whether you say that Z and R have same number of elements,
Oh, so one's uncountable and others countable.
and what about Z and some NZ,
They both are countable. So,
and they have the same cardinality, and they are isomorphic to each other, right?
yes.
So any subgroup, non-trivial subgroup of Z is actually isomorphic to uh, the group itself in Z. So whether they are same as sets, for example, 2Z does not contain odd integers, right? You're okay with that? So if you consider the subgroup 2Z, then it has no odd integer. But inside Z, odd integers are there. So if you look at the size, then uh, counting wise, as such, like if you look at this, whether this element is there or not, then that is not a good measure because both of them are infinite, and how you can compare two infinite numbers. So that's why the card concept of cardinality is there. So in terms of cardinalities, they are same. And in fact, they are isomorphic.
Sir, so are if I have any two countable sets, does that mean that they both have the same cardinality?
To any two?
Any two countable sets?
Yeah, both of them have bijection with the set of natural numbers, right?
Yes.
So if both of them have bijection with the set of natural numbers, means they have the bijection with each other, right? bijection, the property of having bijective maps is transitive relation.
Yes, sir.
So they will have a bijection, then that means they are of the same cardinality.
And is this true for uncountable sets
No.
also?
So there is a statement which says that uh, cardinality of any set A is less strictly less than cardinality of the power set of A. You know power set?
Yes, sir.
So if you take A to be an uncountable set, for example, say R, then power set of R will have cardinality different than R, but both of them will be uncountable cardinalities, right? If something is uncountable, its power set will have uncountable cardinality, right? It cannot shrink. Power set will have more cardinality. Is it fine
Yes, sir. I think so.
or you are lost?
Slightly, but I think I'll just think about it
So
for the next class.
you know that R is uncountable, right?
Yes, sir.
Now I'm saying that there is a statement which says for any set A, cardinality of A is strictly less than power set of A.
I
Right?
don't know why this is true though. So
See, in power set, anyway, the singleton sets are there, right? So it is
yes.
less than equal to, that is fine, right?
Yes.
Less than equal to part is fine.
Yes, sir.
Now for the strict less than, you need to, it's not trivial. It's a very good proof. You can see that that cardinality of A is strictly less than cardinality of power set of A. You can go and check it. Less than equal to part is clear because that power set part will have singleton sets, right?
Yes, sir.
So, but I'm saying it is also strictly less. Now, if you take any uncountable set, then that set, as compared with the power set of that set, will have cardinality strictly less than, right? So, uh, R will have strictly cardinality of R will be strictly less than cardinality of power set of R. And if this is uncountable, this has to be uncountable because it is more. It cannot be countable. So this is an uncountable set and this is uncountable set, but they have the different cardinalities. Now it is clear.
Yes, sir.
And in fact, if I remember correct, then there is also one statement which says that once you have infinite sets, then cardinalities are increased in this way only. So this is two times uh, cardinality of set of natural numbers. So just before that is set of cardinality of rest, uh, natural numbers. So this is countable cardinality. Then you have R, which is uncountable, and this is minimal uncountable, means there is nothing in between. So there is nothing between here, and then once you have this, you will move like that only. So there is also nothing between here and so on. The cardinalities move like increase in this way. You have some cardinality, and then its power set has some cardinality, and so on. So this part is, I think, this part is already there in literature, and but whether there is something between that or not, between R and PR, I'm not sure about it. But definitely this forms an increasing sequence. right? Now you can check whether you can have some set which is of cardinality between these sets, uh, that I don't know. But at least this much is clear that I think between N and R there is no intermediate set, if I remember correctly. Maybe I may be wrong as well, but definitely R has this cardinality, two times cardinality of N. Okay, so maybe I oversaid something, but at least your doubt is clear, right? You said that you asked that whether two uncountable sets can have same cardinality. So the answer is no. And this is the counter example. Cardinality of R is not same as cardinality of power set of R, but both are uncountable. Okay.
Okay, sir.
And all this is happening because cardinality of A is strictly less than cardinality of power set of A, right? So this is a very good theorem in set theory. You can check that.
Okay, sir.
So you have this increasing uh, chain of cardinalities, and uh, I don't know whether something lies in between or not. Maybe that's an exercise. Maybe it's an open problem. I have no idea that whether there is something lying between A and power set of A. When it's finite, then definitely there will be sets, right? When A is finite, then there are many sets which are of between A and power set of A. Because say if you have A to be set of elements, size of A to be n, then size of power set of A will be 2 raised to n. So there will be many elements, many sets which are between uh, having size between n and 2n. But once we go to infinite set, I don't know, means whether there are sets which have cardinality greater than A but less than power set of A. And in fact, I don't know whether the problem is open or solved. You can check it in some set theory book. Some good book, they might have mentioned this, but it's a good question. Okay. Okay. So we just go slightly off track. Sorry for that. Uh, so if phi is a 1-1 homomorphism from Z to Z, then the claim is phi has to be infinite. Why it is so?
So suppose G is some finite group.
So let G be a finite group. Then,
Suppose order of G is n.
okay, let order of G is n.
Since we are considering onto homomorphisms, there will be
Since
uh, some element A, some element G in the group G, such that phi of G equals 1.
so, mm, now, what is the problem if I take G to be acha, order 2 is needed. So this is greater than equal to 2. So let A be some non-trivial element inside G. Then
Oh, so there will be some A in G such that phi of A equals 1.
Y.
Um, so I'm assuming this to be an onto homomorphism,
No,
and then I want to show that
no
there are
is
some
not
contradictions.
from for onto. You can go this with this cardinality argument again. If it is
You,
onto, then the direction will reverse, right? Cardinality of G greater than equal to cardinality of Z. So it's infinite. That's fine. You got my point. For onto, it's easy. Once you have an onto homomorphism, then this direction will reverse. Then there should be more elements here than this. Because for each element
Yeah.
inside Z, there is a pre-image, and the map is well defined. So one element cannot map to two elements. So the size of G has to be greater than equal to the cardinality of Z for onto case. So then G is infinite, that is fine. From here as well you can get. And from that for, A equal to phi 1 argument also you can get. But now why here G is infinite? So that is due to since image of phi is a subgroup of Z, right? That is always the case. Image is always a subgroup, right?
Yes, sir.
Kernel is a subgroup of the domain and image is a subgroup of codomain. You know the proof, right? Identity is there
Yes.
because identity is mapped to identity. For any two element phi b, phi a and phi b, their product is phi of ab, which is also inside image. And for any element phi a, if you take the inverse, then it is phi of a inverse. So image is always a subgroup. So this implies image of phi is equal to nz for some n belongs to z, right? Now since now you know that it is 1 1, phi is 1 1, therefore uh, G is isomorphic to image of phi. Why is it so?
It's 1 1 and on 2. So there's a bijection and
See, you
C
know
is a
the
homomorphism.
theorem, this also simply by uh, first theorem of isomorphisms, yeah, something like that we read, na? First theorem of isomorphisms, group isomorphism, group isomorphism or homomorphism, but that was some first theorem which says that G mod kernel of phi is isomorphic to image of phi. Since kernel is trivial, this is because phi is 1 1. So this is just trivial. So this is isomorphic to G itself. Since kernel is trivial, therefore G is isomorphic to that G modulo kernel phi and which is just image of phi and which is some n times Z for some n belongs to Z. Now it is also given that also size of G is at least 2, right? So this implies n cannot be equal to 0. If n is 0, then there is just one element 0, but uh, G is not of size at least 2, and hence G is infinite. Clear?
Yes, sir.
If it is non-zero, then this set is always going to be infinite, right? So that's the argument. For onto case, whatever you were saying, that was correct. If we have some onto homomorphism from G to Z, then G is an infinite group. That follows by whatever you were saying, or from here as well. From this kind of argument also you can say that if you have a onto homomorphism or any onto map between two sets, then the size of the code domain is greater than equal to size of the codomain. And since the codomain has infinite is an infinite group. So this has to be an infinite group. There the equality will change. That is also fine, or whatever you were saying, that is also fine. Okay. Okay. So that finishes this assignment two. Uh, Maybe we can first discuss your problem, and then if time permits, we will discuss some extra questions. Okay.
Okay, sir.
So in problem, which problem you want to discuss? Practice assignment 4, right?
Yes, sir.
So, problem number.
Problem number two.
Oh, I couldn't hear problem number.
Problem number two.
Four,
The second problem number two
two.
and
Okay.
the option two. So I don't know why that is true.
This is just mentioning like this. Doubt from practice. That part is also not there in the final assignment, right?
So shall I just check and
Yeah, I can do that. So H is a normal subgroup of order 96, then the quotient group is cyclic. Because I don't think it's there. A similar question is
so
there,
there's a similar question. So sorry, it's okay. I think
but what will be
it's okay
the,
if we discuss next time also after the solution is released.
just a minute, what will be 546 divided by 42? This will be, yeah, it will be 13. Yeah, if I tell you this answer, then you will definitely guess that answer also. Why you think that that is not true, or you are saying that it's true?
Oh, so there's no specific reasons. So in the practice assignments, we get the answers immediately,
Yeah,
right?
yeah, that I know. But uh, here, what is your guess and what is the answer coming?
Um, I don't even know how to think about this specific one. So
Then I can't help. But if you get this, then the same trick will work there. That much hint I can give. So this is true or false?
um, I know that this is true, but I don't know why. So
See, you don't have many sufficient conditions for a group to be cyclic. How many uh, uh, statements you know which says that if the subgroup is of uh, that particular kind, then the sorry, the group is of that particular order or the particular type, then the group is cyclic. How many such statements you know?
If there's some generator, then if there's some element A such that A power
You're
n,
not giving any given any element here, right? What you are given, the order of the G and order of H. So it should be based on just the order, right?
yes.
You getting my point? So it's an arbitrary group, arbitrary subgroup. Only information that is conveyed to you is the order of G and the order of H. You know how order of G by H is related with order of G and order of H?
Yes, sir.
How? What is the order of G by H?
That gives the order of G mod H.
Order of G divided by order of H, right?
Yes, sir.
Then you can get.
Okay, sir, I'll try.
All five options I have somehow already discussed in class.
Yes,
This-
sir. The rest of them are easy.
For element of order 2, we saw some relation. And at the same time, I told you that that can be generalized to something. And that generalization fails when you take order 9 elements, right?
Yes, sir.
And here also, you just need to see what kind of the order here, what kind of order it is. I won't say anything more. Even you know that in this particular case, you know that the what is the order and how the groups of that particular order look like. So forget this G by H. Take it just as a group, and you know the order of that group. You know the order of this G by H, right, Prerna?
Yes, sir.
And then what are the possibilities for groups of that order?
Sorry, I did not. I,
You
I don't.
got it?
Not yet.
Then you need to try. I
Okay, sir.
can't give more hints than this. So we are not discussing this problem
Okay.
because it's clashing with the uh, assignment problem. Okay. But both the questions are similar, and once you got this, then definitely you should be able to answer that problem as well. Okay. So we have some time left. So maybe I can discuss some similar problems from the previous year assignment. Oh, but it's an assignment in solutions also. Okay. So you can see the question, right?
Yes, sir.
So G, so we need to determine whether in the following cases H is a subgroup of G. So let me write it as extra questions. So what is your guess? For the first part, G is Z with addition and H is a set of multiples of 2024.
This is a foreman, sir. It's
This
same
is
as the.
true, right? We have already done. So
Yes, sir.
this is true. Now, G is the group of non-zero complex numbers under the multiplication, and H is the set of roots of this polynomial. What about this? Is it true or false? Use your favorite trick to determine
One doesn't belong. So,
one doesn't belong. Good. So this is false since identity is not inside H. Identity won't satisfy this, right? What about the next one?
oh,
You have the symmetric group S4, and H1 consists of all map on the identity map and all permutations which send 1 to 2. Then is it true or false?
I think it is false, but I'm trying to find some counter example.
It is false.
I need to find the counter example. I'm not sure.
Hmm. So if you have one map which is sending 1 to 2, and you have another map which is also sending 1 to 2, whether, uh, hey, this is even easier. So identity is already given, so your trick doesn't work here, right? So C part, so you take sigma 1 like that, uh, S4 to S4. Shall I just write it in cyclic notation? You are comfortable with that?
Yes, sir.
So so what we are supposed to check whether the composition of two such elements is again inside S4 or not. So definitely one maps to two, that is fine. Rest things we will sort out later. And here also sigma 2, one maps to 2, that is fine. Now, if somehow we get elements for which in during composition this fails, this particular thing failed, then we are done. So what if we just take sigma 1 equal to sigma 2, but if we take the same element, then in identity is already there. So we cannot even take sigma 1 equal to sigma 2 equal to 1, 2, because their composition will be just identity. So we need to do something else. So maybe we have already seen that their composition turns out to be 1, 3 or 2, 3, right? So sigma 1 composed with sigma 2, that is 1, 2, 1, 2, 3. What was it? This is just 1 going to 2, 2 going to 1. So 1 is fixed. Then 2 going to 3, and 3 going to 1, 1 is going to 2. So this does not belongs to H, right? Because in H, 1 is supposed to be mapped at 2, but here 1 is mapping to itself. Correct?
Yes, sir.
Now what about D? All permutations which maps 1 to 1, whether identity is there?
Yes, sir. This is a group. This is some.
This is
This is a subgroup.
This is a subgroup. Why? So identity is there. First part is done. Second, if sigma 1, sigma 2 maps 1 to 1, then definitely their composition will also map. Then sigma 1, sigma 2 will also map 1 to 1, right? Because uh, one is mapping to the identity, sorry, the letter one to itself. Another is also mapping, doing the same. So their composition, during their composition also, this thing will be preserved. And similarly, if sigma 1 maps 1 to itself, or instead of writing like that, I will just write sigma 1 of 1 is 1, then sigma 1 of sigma 1 inverse of 1 is also 1, and thus we are done, right? So this implies H is a subgroup of S1. Here, H2. Here it is H2. If 5 minutes are there, so I can just discuss one more small question. Let me just find some small problem. Yeah, I got one. You can just leave this 4 marks thing. This is as I am copying it from last year's assignment. So there this mark thing is there. So you can just, or I will just white out it. So you are supposed to choose again the correct statements, and every group of order 6 is cyclic. Whether this is true?
No. S3.
Why?
S3 has order 6. It's not
If
so.
you know S3, then half of the problem is done, right?
Yes, sir.
So, question two. This is false. Example S3. In the second problem also they are giving S3. So let H be a proper subgroup of S3, then H is cyclic.
This is true.
This is true. Why?
Um, I only know the case by case solution. If it's a
Mhm.
two cycle, then
Whether it's needed. So till now you don't know that Lagrange theorem, or you know that you
uh,
don't know Lagrange theorem, right? Or you have
uh,
studied,
yes, sir, I have.
but that will come later, right? In I think after you read these factor groups. So from Lagrange theorem, that would be very easy. But if I tell you the statement, then you will be able to solve that problem also.
So the only possible orders of the subgroups are 2 and 3.
Hmm. Every subgroup of order 2 and 3 is cyclic. And once I told you that every group of prime order is cyclic,
Then it's done. So
then it's done. Okay. You can use it for other problems also. Okay. So, uh, but here we don't know Lagrange. We don't want it to solve by Lagrange theorem because that will come later. Till assignment 2, we have no idea about Lagrange theorem. So here by case thing, you can do that. Okay.
Okay,
So
sir.
this is also correct. You just need to check. Okay. Uh, Now third part is let G be a G be a cyclic group if phi from G to G prime is an autohomomorphism. This you have already seen. For an autohomomorphism from a cyclic group to another group makes the domain to be cyclic, right? This is
Yes.
coming again and again. Every group of order 4 is cyclic, so this is not true. Again, example is Klein's group. So, in fact, so you have the same uh, set of examples, but this gives you one statement that you might be missing, I guess, right? Every group of prime order is cyclic, and I leave it to you to prove this statement. Okay?
Oh, I think this gave the hint to some other problems.
Uh-huh. I couldn't hear.
No, I think this has given sufficient hint to solve the doubt that I asked.
Right. So now you should be able to do that. Okay.
Yes.
But you also try to prove why it is so.
Okay, sir.
If you
Oh,
look at
so
some of the lecture notes, then I have already uh, told you why. If it you have a prime, then you take any non-identity element. I think that will generate the entire group. You start
yes,
with any non-identity element, look at the subgroup generated by it, then that subgroup is already inside the group, and you need to show that the group is generated by that element. So any element is inside the group is of the form A raised to M. And then I leave it to you. Similar kind of argument may work. That division algorithm thing we do now. Or here you can use, since you have already known the Lagrange theorem, so since it's prime, so any subgroup, order of any subgroup will divide the order of the group, right? But the order of the group is prime. So only possibility of numbers dividing it will be just that number itself or the identity. So if you start with any non-trivial element, the subgroup generated by it should have the order same as the order of the group. That means the group is cyclic. Clear?
yes, sir.
Okay. Okay then. Are there any doubts? Uh,
No, sir.
then maybe we can stop sharing and we can end the meeting. We will meet at uh, 6 to 8 in the next class, that is on the next Tuesday. Yes, I think 26. Okay. Okay then. Bye. I'm
Thank
ending the
you.
session. Okay.